Hello everybody, and we are going to get started on waves today, and we're going to get started on wave characteristics. So just some characteristics about waves and the different types of waves and what makes them different. So let's go ahead and talk about in general what is a wave. A wave is a repeating disturbance, and it's usually started by a vibrating source, and that wave transfers energy through matter or space. Now all waves transfer energy. It doesn't matter which type of wave it is. And there are two types of waves. We have mechanical waves and we have electromagnetic waves. Now another name that you might see instead of electromagnetic is non-mechanical. So let's go ahead and talk about mechanical waves, because we're going to actually talk about electromagnetic waves in our very next to last video, but we're going to go ahead and talk about mechanical waves and learn about them first. So mechanical waves are waves that can travel only through matter, and matter, remember, are things that have mass and take up space. Now the matter that waves travel through we call a medium, and there are three types of medium. There are solids, liquids, and gases. Solids are most dense, liquids and gases are less dense than solids. So, for example, a gas that we have waves travel through is air, and sound waves travel from a stereo through the air to hit our ear. Rock, which is a solid, that's a type of medium that earthquakes travel through, and we call earthquakes seismic waves. Water is a liquid medium that waves can travel through, waves on a pond, waves in an ocean, and we call those water waves. All mechanical waves must have a medium. That's the difference between mechanical and electromagnetic. Electromagnetic do not require a medium. Mechanical waves require a medium. And another way to think about mediums are things that have atoms and particles. And think of those as stepping stones, and mechanical waves have to have those stepping stones to be able to travel. Now wave speed, how fast a wave goes, is determined by the medium it's traveling through. A list of mediums from fastest to slowest is as follows. We have solids, which are the fastest, then liquids, and gases waves travel the slowest through. And this seems backwards because we would have thought the other way, but actually solids, and I'll explain why in our next video, but solids waves can travel the fastest, gases they travel the slowest. And there are two types of mechanical waves. We have transverse and we have longitudinal. So let's talk about transverse waves. Transverse waves, particles in a transverse wave move perpendicular. Perpendicular means at a 90-degree angle to the wave motion. So if the wave motion is moving left to right, the particles are moving up and down. Now let's look at parts of a transverse wave. Here's a crest. Here's the trough. Amplitude is usually right here is the medium that goes right through the middle. And so amplitude is from the medium to the crest, or from the medium to the trough. And then you have a wavelength, which is crest to crest or trough to trough. So let's look at the definition of those. Crests are the high points of the transverse wave. Troughs are the low points of the transverse wave. Think of a mountain crest, right? High point of a mountain. Wavelength is the distance between one point on a wave and the nearest point just like it. So crest to crest or trough to trough. Amplitude is the measure of the size of the disturbance from a wave. So if you have a larger disturbance, you're going to have a larger amplitude. A less of a disturbance, less amplitude. And then the frequency of a wave is the number of wavelengths that pass a fixed point each second. Now you can find the frequency of a transverse wave by counting the number of crests that pass a point each second. And we'll talk about how to find frequency on a longitudinal when we get there. So wave behavior. When energy increases, then your amplitude increases on a transverse wave. When your energy decreases, the opposite happens as well. Amplitude decreases. So when energy increases, amplitude increases. When energy decreases, amplitude decreases. So let's look at this. Low energy wave it is closer to the medium. This is considered the medium, this line that goes through the middle. And the crest and the troughs are closer to the medium in a low energy wave than a high energy wave. High energy, higher and larger amplitudes. When frequency increases, wavelength decreases. So the faster it's moving, or the more it's happening, the wavelength gets smaller. And when frequency decreases, the wavelength increases. So these have an inversely proportional relationship, meaning when one increases, the other decreases. So they have opposite relationships. So let's look here. Here's a high frequency wave, and here's the wavelengths. Do you see going from one crest to another crest with my pointer? That's a wavelength. Down here, a low frequency wave has a much larger wavelength than the high frequency wave. Oops, sorry. So on low frequency, large wavelength. High frequency, smaller wavelength. Now some examples of transverse wave. Water waves and seismic waves are transverse waves. Now let's talk about longitudinal waves. Longitudinal waves are still mechanical, and they have particles that move parallel to the wave motion. So if the wave motion is moving left to right, then the particles are also moving left to right. These waves are also known as compressional waves and parts of a longitudinal wave. We have compression, when the coils are really close together, and then we have rarefaction, when the coils are more spread apart. And the wavelength is when you go from compression to compression, or rarefaction to rarefaction. So let's look at those definitions. Amplitude on a longitudinal wave is measured by compression and rarefaction. Those are considered the amplitude on a longitudinal wave. Compression is when the coils are bunched up. Rarefaction is when the coils are stretched out. High amplitude waves have very tight coils in compressions, and they're farther apart during rarefactions, and the opposite is true for low amplitude. Less tight coils, you're still going to have compressions, but they're going to be less tight, and they're going to be closer during rarefactions. So let me show you an example. See up here, high amplitude, we have close compressions. This is a compression down here on the low amplitude, but do you see how they're less tight than the ones on high amplitude? And then rarefactions, you have more spread out as well. Okay. Now the definitions of these parts of a wave. Wavelength is the distance between one point on a wave and the nearest point just like it, and this is the same definition from transverse. The same definition from transverse also is frequency. Frequency of a wave is the number of wavelengths that pass a fixed point each second. So you can find the frequency of a longitudinal wave by counting the number of compressions that pass a point each second. Now, this is an example of high frequency longitudinal wave and low frequency longitudinal wave. This is the same time frame, but do you see how you have two wavelengths in the same amount of time as one wavelength on low frequency? So low frequency, you're going to have less wavelengths, right, or larger wavelengths. High frequency, you're going to have smaller wavelengths, and they're going to be happening more often. Now, some examples of longitudinal waves are sound waves. So our next video is going to be about sound, and anytime we talk about sound, we're always talking about longitudinal waves. Now, seismic waves can also be longitudinal. So seismic waves can be longitudinal or transverse. Now, it's time to go ahead and summarize for this video. So this is what I'd like you to do. I want you to set a timer on your phone for 2 minutes, and I want you to write as much as you can in 2 minutes that you've learned from the video. All right, I hope you have a good evening, and I'll see you in class.